Okay, so we just had a question about plugins and scripts. So let's talk about that. We'll look here what's on the topics of interest. Plugins, scripts, where do we find them?
I think it's on the second line.
Oh yeah, applets and plugins. That's what threw me. Okay, sure. Did you want to talk more about scripts, or do you want to talk about applets and plugins?
Scripts and plugins, and we can include applets.
Okay, the whole bundle of stuff all together. Sure. Okay. Well, to start with, plugins generally. Okay. Plugins generally are applications that, alongside a browser, because they provide specialized features that ordinary web browsers do not. And typically the big things with that, typically video play or enhanced graphics. Okay, so that's what plugins. Now there are a variety of other plugins for other things, but that's the big kind of stuff that ordinary people are familiar with. Now, all plugins sometimes need to access browser data effectively. For example, in order for a video game to upload your scores to Facebook or send notifications to your friends, it needs access to some browser data. Ideally, automated security features prevent the plugin from accessing anything it shouldn't, but that's much easier said than done, right? These systems are complex and their designers are fallible, right? They make mistakes. So, and this is true. This applies to all plugins, and applets are just plugins written in Java. Okay, so this applies to applets just as well as it applies to other plugins. There are security vulnerabilities inherent to the possibility of allowing some other application access to your potentially sensitive browser data. Now, alternatives to that, okay, as an alternative to plugins, HTML5 has provided some enhanced capabilities previously only usable through plugins. Okay, again, basically advanced graphics, that sort of thing, and video play. So once, for example, YouTube used to use Flash, but now is through HTML5. Okay, and you can find other examples too. Your favorite Facebook or other web app games, now the same. Okay, for example, for years I used to be able to do Angry Birds as an example of plugins, but lately when I go to do Angry Birds on this machine, it says, yeah, it still uses the plugin, and this machine has it disabled, and blah, 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 so it's kind of a hassle. So a lot of these kind of web apps, they've shifted over away from Flash to other HTML5 usage. All right. This is provided through scripting languages. Now, of course, plugins can use scripts, of course, to do a lot of stuff they do, but the difference is in a plugin, it's still a secondary application. So this is provided through scripting inherent in the browser itself, right? That can be that can be processed inherently by the browser application. Most of the things you'll see will be JavaScript. Okay, we did that in lab exercise 12. Java exercise, client-side script. Basically, the code runs on your machine. Okay, it's and is largely written into the web page. The other, PHP is a server-side script. And essentially the way PHP works is the web server runs the PHP code before you get the page. The PHP converts somehow to HTML. For example, pulling data from a server and constructing an HTML table from it. Okay. Then the user sees the completed page, but never actually sees the script code. Okay, so that's pretty much it. That's pretty much what there is to say about plugins, scripting, all that. Okay.
Thank you.
You're welcome. Oh, look, we got so many chat bombs going on. Let's see what's going on. Fingerprinting. Okay. Wow, we got a lot of stuff. Okay. I see people are typing in stuff. Security vulnerability prioritization. Okay. So that's our next one, security vulnerability prioritization. I see we got a bunch of topics to go on. So, all right. Suppose you are some sort of online criminal, okay? And you don't have a specific grudge against any person or entity. You're just looking to get some valuable data and sell it, and don't care much who it's from. Okay, this is the typical profile of an online criminal. There are certainly ones that are motivated to target specific operations because they have some kind of big grudge, but the more common profile is they don't really care who they get as long as they get somebody. So how would you go about picking which vulnerabilities to target and exploit? Okay, well, number one, more victims means more dollars, right? All else equal. Number two, more valuable data means more dollars, all else equal, okay? And number three, greater chance of success per attack means more dollars, all else equal. Okay, so the ideal target would be, number one, a highly popular application or platform, right? Something that everybody uses, like, for example, Acrobat for PDFs or Microsoft Windows as an operating system. Okay, that would be one. Number two, more valuable data. If you can hack, say, a banking system, that's much more valuable than, say, what would be a low priority target? Then say, I don't know, think of what would be a small lawn care business. Okay, lawn care business might have some money, might be worth doing some kind of extortion on, but banking, if you can hack that and you can start dribbling money out of people's accounts, well, there's some real money there. Okay, or similarly, or any financial data, probably more valuable than Facebook passwords. All right. And greater chance of success. Well, what means a greater chance of success? Number one, if you can specifically target vulnerable people, say through phishing or other mechanisms, okay, that's one possibility. Or number two, an application with a vulnerability not included in any patches yet, right? A so-called zero-day vulnerability. That's probably going to work pretty well. Okay. Or number three, if you can get people to install the application themselves, like that Flash Player one, right? The Flash Player clone. Okay. All those are, you know, sensible options. So when you're prioritizing targets, if you want to make money, obviously you want to pick an application that's popular or a platform that's popular so you get more victims. You want to pick data that's valuable for its own sake as far as you can get it. And last, greater chance of success, right? If you have some kind of attack that you're probably going to succeed with, that's going to be better than something that's, say, a long shot. Okay. So this is why you see things, you know, again, once upon a time, so concrete example, once upon a time, applets were widely targeted for attacks. When applets began to, typing is hard, began to fade away in favor of Flash, well, guess what happened? Then Flash itself was often targeted. And then with the adoption of HTML5, making Flash somewhat unnecessary, there was a corresponding rise in things like phishing and ransomware attacks. Okay, because people are going to go with what works. Okay. I hope that is sufficient. So next thing here, we got Dash. I'll talk about Dash for a minute. Core idea about Dash, right? So remember, dynamic, adaptive streaming over HTML. What it's doing is trying to keep a video stream playing continuously despite variations in connection quality. Basically, we'll sacrifice some resolution or frame rate in order to keep the video going. All right. So the way it works, YouTube, for example, other places use Dash, but YouTube will encode video segments to different quality levels, each requiring more data, right? So again, if you have highest quality or high, medium or low or lowest, they might require more data that looks something like this. Highest is going to require a lot. High is going to require maybe half as much. Medium, maybe half as much or so of that. Low, half of that. And lowest, well, the lowest, maybe half of that, give or take. Okay, just to give you an idea of what they're doing. Now, over time, your connection rate may change, right? Suppose you're out there, you're walking around. Sometimes within a building, you have a very good wireless connection. Sometimes it's awful, like the nearest wireless access point is behind a couple walls, whatever. So as you're moving around, you might experience some periodic changes. Can I change that? Good. Okay. Not there. That'll do. Okay. So you might see something like this, right? And here I'm going to put in connection quality. And by that, basically, we mean the data rate, how much traffic you can get on your particular device. So YouTube or Dash, right? Dash on YouTube will send you the best quality segment it can, as long as it doesn't make a big dent in your buffer. Remember, YouTube buffers the data, keeps sort of an ongoing pile of data in your browser so that it can keep playing the video continuously, even if you temporarily lose connection, for example. So that's basically what it's going to try to do. So if your connection rate is really good here, at first, YouTube is going to send you one of these, right? And you say, oh, great, thanks, YouTube. Whoop. There we go, got it. At first, YouTube, you're going to say, oh, great, thanks, YouTube, okay? But then we get to this point, and your connection is starting to lose a little bit of quality. So, okay, YouTube sends you not quite as good a copy, okay? But it sends you one enough to keep you going for a while. As you go, oh, by the time you're ready for the next copy, the next segment, you're terrible, right? That's what your segment looks like. So, let's see. Can I even grab this thing? Guess not. Maybe it's going to send you one that looks something like that. As time goes on, your quality gets even a little bit worse than that, and it's going to send you a very low quality one. Okay, that's just enough to get you through the next, whatever, 5-10 seconds or so. But as you get over here, hey, quality starts to get better. So YouTube says, hey, look, now we can send you this segment. And that's great. That ought to make you happy. And then at some point down the road, eventually, your quality, your connection quality gets excellent again, and you're ready for this one. Okay, so we have some big, I'm running out of a little space to put it in, but you get the idea. If I wanted to, I suppose I could capture all this and just slide it backwards a little bit. There we go. Beautiful. And something like that. Okay, so that's the idea with Dash. It's pretty simple. I mean, the implementation details are not necessarily simple, but the underlying logic of it all is. Okay, let's see what else we got here. Transmission scheduling mechanisms. Okay, well, there's not much to say about transmission scheduling in IDS 201, so I'll get that out of the way first. You don't even need to know that binary exponential backoff thing. It's just something that I like to mention to give people something to talk about at Thanksgiving or Easter. It happens during the spring break time in the spring semester. Anyway, so what can we say about transmission scheduling schemes? why do we need them? Why do we need them? Why bother regulating when devices transmit? Okay, that's a fair question. Well, the answer is this. If there wasn't any regulation and devices all transmitted whenever they felt like it, right, we can say without regard to other nearby activity, a lot of the packets would be received in some garbled state, right? So number one, garbled data is unusable. And number two, you'd need to retransmit, which would make the problem worse because everybody would then be trying to transmit all the time. This is a big problem. Okay, so that's the short version. Why do you need them? Because if you didn't, then different devices' transmission attempts would often interfere with each other, and the result would be garbled and unusable. Now, how do devices do it? Well, typical way, there are, first of all, there are many different transmission scheduling schemes. If you were taking a CS course that covered this, you'd learn some of them. But this is IDS 200, right? We're not that worried about. The key thing is simply to understand devices take turns in some fashion. For example, one possibility is the binary exponential backoff that we talked about a while ago. Basically, devices take turns listening to the channel prior to transmitting. Okay? If the channel is busy, right, somebody else is transmitting, they try again later. And typically with and at longer intervals. For binary exponential backoff, it doubles. Okay, so that's what happens there. And the goal of binary exponential backoff is if there are more devices transmitting more often, then what will happen? Then the actual transmission intervals will be longer. Okay. On the other hand, if you're talking about something like TCP, right? Generally, with TCP, a device that has already claimed the channel will tend to keep sending data continuously until it's done, because that's more efficient than trying to regulate who's next to transmit for every packet. Okay, so that's another way to do it. So this one, binary exponential backoff, it has as a goal essentially fitting transmission rates to active node population, right? Basically, how many devices are doing stuff. And that makes sense for some networks. TCP is typically geared around efficient usage of existing capacity. And you can also have other ones like round-robin schemes, I'll mention. Round-robin schemes will try to guarantee that every pair of devices, every node pair has an opportunity to transmit within a given time interval. Okay, and so the idea one there, it's not so much about efficiency and it's not so much about fitting transmission rates, but this one is about some kind of guarantee of equal access to the network. Okay, and depending on what your network is doing, what it's for, who it's owned by, any one of these could potentially make more sense. So, transmission schemes, what they are, they're how devices regulate when they're going to transmit. I'll add in one more point. This function is managed by the data link or link layers, right? For OSI or TCP IP. Okay, so that's what there is to say about transmission scheduling schemes. Okay, see we got a bunch of stuff here. Let's roll this up a little bit. So cookies, copyright checking, violations, we got a bunch of stuff. Profiles, okay. So let me ask you, if Kelly, are you there? Are you here?
Yes, I'm here.
What is there anything specific? That's a lot of stuff there. Is there any specifics in there that you're concerned about?
Can you do the cookie and the last one, the with the system?
Yeah, Vitesse. Okay, we'll come back to those others, time permitting. Okay.
Okay.
So cookies, sure. Cookies. So first of all, there are two types. First person cookie added by a website to be used on that website. Okay, for example, Amazon storing contents of your shopping cart, or YouTube tracking your current play location on a video. Okay, those are all possibilities. So first person cookie added by a website to be used on that website. A third person cookie added by a website to be used by a different website. So for example, suppose Yahoo has partnered with Amazon to show Amazon's ads, and those ads, those ads will be personalized to show items you've recently viewed. Okay, so when you visit Amazon, Amazon adds a third-party cookie to your machine with that data, right? The things you've looked at recently. When you visit Yahoo, Yahoo can access the cookie Amazon put on your machine and use it to display relevant ads customized for you. Okay, that's a third person cookie. The other one is a super cookie. And the easiest way to think about a super cookie is that it integrates data from multiple cookies, typically owned by the same organization. For example, Facebook might pull together all the data from various apps or business partners to get a better composite profile of a user. Or Google, same thing, right? Or Google would pull together data from all your different machines and browsers using the full set of Google applications and platforms. Okay, so those are your three kinds of cookies. We can also ask, what is a cookie? What is a cookie? Well, short version, it's a small file capped at about 4K for ordinary HTTP cookies. Okay. Typically will contain a mix of encrypted and unencrypted data, right? Like in the example in the slides. But if it contains any sensitive data at all, then much of the data will be encrypted, right? So, like I said, in the example in the slides, it was from udacity.com, and you can see a little bit of stuff in there that's unencrypted, right? The words Udacity, for example, and some stuff about the user ID, that's all in there. But the actual contents of that, you know, is all encrypted. So that's pretty much it. That's what a cookie is. Any organization that places a cookie on your machine can have its own unique arrangement of data, right? So typically, what you'll see is a list of variables and their values. So for Amazon, might be list of items in your cart, list of items recently viewed but not bought, and you know, those are probably the big two there. For YouTube, list of currently playing videos and the, you know, and how far along they are, and list of all recently watched videos, right? If you go to something like eBay, oh, and I guess, you know, I should probably mention access credentials are probably in the Amazon cookie, and likewise, same for YouTube, access credentials, which are obviously, you know, these first two may be sensitive, access credentials, definitely sensitive. Okay, same thing for YouTube, right? Maybe the list of videos that you're watching is sensitive, maybe not, but your access credentials, again, definitely sensitive. So probably all this data is going to be encrypted in some fashion. Okay, so a little bit of it is sensitive, then to make it harder to find what of it is sensitive and what isn't, they're just going to pool it all together. Okay. Let's see, where were we? And then Vitesse, okay. So YouTube does have quite a few batches of data to store, right? The big ones are going to be things like the videos themselves segmented, and part two, the video metadata. Okay? Now for these, Google can use an ordinary relational database. If it wanted to, it could also use user comments, and user accounts. You could have other things like list of subscriptions, stuff like that. Sure, I'll add that. Lists of subscriptions, and I suppose probably playlists too, although those might be stored in cookies. But let's say they're stored. User information, okay? So all of these can be handled reasonably well by a relational database, but like Google, with some extensions. So again, Google, they use a system built on top of MySQL, which is a relational database platform. So Google has something called NewSQL that has extended features beyond what's available in ordinary SQL. But basically, it's a relational database that has some special features in it. Okay, so the reason why, and that's Vitesse. Okay, the reason why you can handle it as a relational database is, number one, why you need to. YouTube wants to let its users run queries involving multiple tables, right? So things like, give me the list of all videos by a particular artist or YouTuber, right? What else? Give me the list of all videos. What's another one that we could do? I'm thinking. I guess if I were going to do this, I should say, you know, the videos and the metadata. That anytime that's linked. Okay, so list of all videos. I'm coming up a little blank here. I'm not sure why. Oh, all videos created by common viewing, right? So example, people who viewed this viewed that. In order to provide that sort of information, you need to run queries across tables. So that's fine. Okay, number two. So YouTube wants to let people do that. Number two, with a NoSQL type system, those sorts of tables probably not feasible, right? Unless you have the relational aspect in there, in which case it's still just an extended relational database. So a NoSQL system like YouTube use, for example, Facebook's Haystack allows efficient storage and retrieval of data, but not much for multi-table queries. All right, so what else? That's what YouTube wants. That's why a regular NoSQL type system isn't really feasible. It's efficient for storage, but again, the fact that you could have different data formats like in a key value store, it would take too long to do multi-table queries. It would be very, very slow. Okay, other additional features, query parsing and overlap checking, for lack of a better word. So for example, if two queries return the same videos, they're functionally identical, right? So that's something that YouTube could learn. Likewise, if one query is a clear subset of another, right? So for example, videos from 2015 is a subset of videos from 2010s, right? Then again, the query doesn't have to be run from scratch, but can use cached results already available. Okay, So that's the sort of thing, right, that you allow with this extended relational database. Number one, you can do multi-table queries, right? That you can do with any relational database. But specifically for YouTube system, what they want to do is not have to run the same query over and over when the cached results are already available. So they also include this feature where it can analyze the queries themselves and say, is this query basically equivalent to one, or is it a subunit of another? And that's some key functionality they put in there. Okay, so that's what we have to say about Vitesse. So again, Vitesse built on a relational database platform, right? MySQL, but extended, like again with query parsing. Okay, so we'll come back to some of this other stuff if time permitting. YouTube video caching strategy. Well, that's a pretty short one. So YouTube wants to keep videos stored close to their interested users. Right, that makes sense. Again, just like Facebook stores user data in data centers near those users, right? Big reason, response time is faster, and number two, there'll be basically an apples to apples comparison for what's popular. Okay, so for example, if I had, imagine if YouTube had a data center that covered both Japan and the US West Coast. Well, part of the time, the Japanese users would dominate, right? There'd be a lot more of them, and Japanese content would be prioritized. Okay. The other times, right, part of the time, US users would dominate. Okay, and US content would be prioritized. This would create a need to constantly churn what's popular and what isn't, okay, which you don't really want to do. Much more efficient, read easier to manage, by giving Japan its own data center with fairly constant preferences, right? I mean, of course, they're going to drift over time, but you assume the people that watch stuff in the evening are watching about the same stuff as in the morning. And likewise, giving the US West Coast its own data center. Okay, same kind of thing with YouTube, right? Well, that is, I was giving YouTube as an example. So what YouTube wants to do again, store user data near users that are interested, figure out what's popular. A lot of this is simply driven by local language. Largely driven by local language, but just like with Google Pages, videos can be popular enough to be stored at multiple data centers, right? So for sure, there's enough popular American music that, you know, gets watched worldwide and will be stored on data centers worldwide. Okay, but for the first baseline of stuff, yeah, if something is written in a local language or especially if it's an obscure language that only maybe 5 or 10 million people speak, then yeah, it's going to be stored at a data center there because you're not going to find many users around the world that are otherwise interested in it. Okay, let's see. So quality of service measurement, problem causes consequences. Okay. I feel like I covered all this in another course this week. All right, so quality of service. So big things to keep in mind. Number one, quality of service is not a simple monolithic variable that means the same thing at all times, right? There's a couple of different ways to look at it, right? It could mean, in absolute terms, could mean good data rates in absolute terms, could mean subjective performance, like are users happy, okay? And applies not just to raw data, but to number of applications or users or connected machines, right? Any of those could be a problem. So quality of service is one of those things that, again, it's a little bit tough to measure. It often gets used as a catch-all. Especially in advertising, right? So you'll hear the various cell phone providers saying, our network provides the best quality of service. Well, on what metrics? That's a fair question. Do you have the best coverage, or do you have the best, lowest rate of calls dropped? Do you transmit the most data per conversation? All of those could be different ways of looking at it. Okay. So there's that. That's the first thing about quality of service. But basically, when we talk generically about quality of service, we typically mean that enough data is getting through that the applications are all functioning the way they should. So for example, emails get delivered in a reasonable time, not split seconds, but in a reasonable time. Voice over internet is pretty much in real time, close to zero lag. Okay, online games as real time as they need to be. And so on. Okay, so again, depending on the application, what constitutes adequate quality of service is kind of up in the air. Even simple things like Facebook, we brought up, if I shouldn't say simple, but everyday example. So for Facebook, quality of service will focus much more on download times, right? How quickly your feed loads, for example, as opposed to how long it takes to upload a new image, right? Where some delay is, you don't want it, but it's tolerable because most people, they don't spend that much of their day uploading pictures, and if it takes a little while, so be it. Everybody on Facebook, though, wants to have their feed load quickly so they can do stuff, so that's what Facebook focuses on more. Now, if your quality of service is bad, okay, so suppose, however you're going to measure network capacity, most quality of service troubles are caused by insufficient capacity relative to needs, right? So for example, too many users running too many applications, trying to do too much. However you want to break it down, there's too much stuff going on in the network and the system can't handle it. So when that happens, it's analogous to a traffic jam. The traffic moves along slowly, and nobody's very happy. So what are some things that can happen? Well, number one, we have lag, right? Latency, basically how long messages take to get to their destination. Okay, so anytime if you're playing some online game and there's a bunch of people connected to your server and everything's really slow, you say, oh man, there's so much lag today, right? That's because all the packets that are describing what you're doing, they're taking a while to get processed by the server, and when the server responds back to you, that's taking a while too. Number two, jitter. What can happen is variability of latency across packets for a particular application and user. So if you're getting latency, right, latency will mean, say, every packet takes 5 seconds to get to where it needs to be, but it'll be predictable. Okay, it's a predictable slow thing. Jitter means maybe some packets are arriving very quickly, but every now and then you get one that's, you know, maybe 5 seconds. And latency, I'll add, typically caused by many users with equal priority. So nobody has a first in line status for the application, but the application can only push through so many packets per second. So if a lot of people are asking for data, everybody's going to experience being slow. Jitter is often caused, I won't say typically, but often caused by users with varying priority in a busy network. So for example, if user A has top priority and doesn't use the network much, but when he does, he pushes all other traffic to the back, right? He pushes all other traffic off to the metaphorical side. Then another user, B, will experience that as varying latency, right? Sometimes quick, sometimes slow. It can be caused by other things too, but again, also by rapidly changing traffic levels, rapidly fluctuating traffic levels. For example, every now and then, a bunch of applications all try to send in some update, and that slows everything down for a bit. Okay, but again, it only happens every now and then. So most of the time things are going along fine, then boom, all these applications want to do some stuff and everybody has to wait. Even whether the applications are equal priority or higher priority, it's suddenly the network is going to be busy and everybody's going to feel that. Last thing can happen, packet loss. So when packets are stored at intermediate locations on a routing path, right, or even on a switch, when they're stored at intermediate locations in transit, sometimes there can be a backlog, right? So these devices generally have some memory where they can temporarily store incoming packets, but if the backlog is sustained and severe, eventually that memory will be overloaded, and the packets will be dropped because the next one in, right, because the next packet received will either push out an old one or itself be discarded because there's not enough room to store it due to insufficient memory. Okay. So those are three problems, right? And basically, all of those are obviously pretty bad. Latency and jitter managed by buffering at YouTube. So again, YouTube buffers a bunch of data for any video that you're currently watching. So even if something goes wrong, there's time for it to recover. Same thing with packet loss. As far as packet loss, remember, with TCP, there will be some retry attempted. Okay, with UDP, nope, the packet's just lost. Okay, so remember, TCP does attempt to run packets that don't get through. All right, let's see what we got. We probably got enough time for one or two more things. Okay, fingerprinting. Fingerprinting is an easy one. So the short version in 2020, right, even a few years back, cookies are still used and useful, but not like they once were, right? So we have more users blocking or erasing cookies. We have users have multiple devices. Users use incognito mode in various ways. Incognito mode, private mode. Okay, and a shift from ordinary browsing to dedicated apps. Right. So, for example, like the Amazon app, instead of visiting the website. Okay. So, because of all that, cookie data is splintered over multiple machines or apps or even time intervals. Okay, so as an alternative, some websites are trying to use fingerprinting essentially by reading the user's hardware profile, because hardware is often varied enough that not many users in a given area will have precisely the same. Okay, and you can look at that in all sorts of things. For example, you can include the machine itself, possibly the screen, size, and manufacturer. Okay, what else? Potentially, hello, what's happening, sweetie? Oh, me too. Or other system parameters. Okay, so some sites will try to uniquely identify and track users using fingerprinting. Okay, that's about what there is to say about that. I think we have time for one more. Yeah, you're welcome. Okay, so let's get back to that then. Copyright checking violations, user profiles. Okay, we'll see. We'll see if we have time for all these. All right. So the overall philosophy at YouTube is that if you didn't create the content, you shouldn't make money from it. Okay, and that's a practical way of dealing with various legal challenges. Okay, so in general, number one, detection. YouTube maintains a database of content, and when you upload something, YouTube will check if it's already been created and registered by someone else. Okay, kind of like the Shazam app, if you're familiar with that. I think there's an exclamation point with the Shazam app. Anyway, I could be wrong. Where you can have it listen to a song and then tell you who it's by. Okay, and then consequences. If YouTube determines that you are not the owner of the content, it can allow the owner or creator to run ads on your copy of the video or block it entirely. Okay, there. So that's pretty much it. And last thing, going rates. I think that was the last thing. Yeah, use video revenue. User profiles. Well, user profiles, there's not really much to say about that. YouTube, just a few minutes, sweetie. YouTube tracks what users are doing so that it can offer them better recommendations based on what it thinks they'll be interested in. And a lot of that is the same way recommendation systems in Amazon work. That basically, so in terms of user profiles, YouTube wants to be able to show or recommend videos that you'll click on and watch. To do that, it needs to track what you've actually watched and what similar viewers have actually watched. Okay, that's sort of data. So again, very much like Amazon. Part of your recommendations are based on your actual viewing and purchases, and others on people who viewed or bought this, also viewed or bought that. Okay, so that's essentially the point of user profiles on YouTube. So we have one more, and then I guess we're done. Last, video revenues. Okay, so typical revenues, probably a few dollars per 1,000 views. If you're running reasonable ads, right? If you're running typical ads with typical response rates. Now, at the low end, the numbers tend to be higher, right? Once you get into the many millions of views, it tends to drop, right? But still, not much below $1 per thousand. Okay, so those, again, those are typical numbers, but there's wide variety in how much the clicks are worth. Just to, I don't expect people to fully know this for the exam, but for example, popular terms, popular ad categories, high-paying ad categories will be things like, one second, things like life insurance or insurance generally, because people are signing on for a long stretch of it and they usually only look at it when they need it, right? Same thing for student loans. Those tend to pay very well. Legal or medical advice, real estate, okay? Anything that's fairly expensive and people are likely to search for only when they're ready to buy, right? I mean, most of us, we wouldn't go around just randomly looking up legal services unless we were in a situation where, yeah, we actually need it. So these sort of things, these tend to be substantially higher. But if you're talking ordinary, yeah, ordinary ad categories, this is around a good figure. Okay. So we have reached the end of our appointed time. I think we covered everything, so that's super. And I'm going to stop the recording. It's been a hoot. I'm going to stop the sharing, stop the recording.